All right, we'll start with some examples using the left, right, and midpoint summation. I'm gonna pick a couple from the book, just to make sure y'all know what you're doing. You wanted specifically midpoint, right? So y'all wanted to see the midpoint thing? Okay, let's see, one of the examples, I think this is number 16, why not? Alright, they give us, I believe it's x squared plus x on the interval from -1 to 1. Do not assume that because it's -1 to 1 that this particular area is symmetric. It would be nice, and later on we'll talk about that, if it is symmetric, that you get to do, half the work, if I can do the easy half and then just double it or something like that. That's not this case. We're gonna treat it like we don't know what the shape is per se. If you want a graph, knock yourself out.
You probably want to hear Michael's chip day in the background.
Yeah, right. That's Michael eating chips, by the way.
I'm hungry.
Yeah. If you don't want to graph it, that's also perfectly fine. For the sake of this example and for the fourth blockers, we'll go ahead and draw a tiny picture.
I didn't graph any last.
You don't have to,
Okay.
please don't. And I'm not, once we get decent at this, but for them having their first example of not really
Okay.
knowing what they're doing, just to show them what the area looks like. So, let's see here, we're gonna have roots at 0 and at -1, okay? So this graph is gonna look something like this. Right. Give or take, something like that. So there's our f of x. And they want us to find, this is an interesting example because of the way the area is above and below. We got a little bit of area from -1 to 1. We got a tad bit that's below the axis, and we got a tad bit that's above the axis. So this together is what we're going to be finding the area of. When we do it, it will have a canceling effect. We're going to treat this like it's negative area because it's below, and this will be positive area. So it'll be averaged out. If the answer comes out to be 0, that means there's exactly the same amount of area above as there is below, and it all canceled. If it turns out to be positive, then there was more positive, negative, more negative. That's technically a section or two ahead, but this is a really good example for doing that. They wanted to do R5.
I don't understand negative area.
For us, it just means below the x-axis. All right, aside here, if you think for a second about maybe a company's profits. Okay, this right here might be where we're gaining money, and here we're in the red, we're losing money, and then you'd be back to gaining money again. So negative numbers just means we're losing stuff. So for us, negative area is going to take on a lot of different meanings later on, but it is good to know that there is such a thing as negative area. Okay, what does R5 mean? Well, the 5 part tells you that we're going to cut this
5 pieces.
weird area into 5 different pieces.
Something like that.
Not the greatest on this particular interval, but whatever. The R tells us that we're going to be using the right sides of the rectangles that we cut. So the first thing we need to determine is the length of each of our bases. Okay, and then the heights. And we're going to do this 5 times for each of the 5 different rectangles. This base is going to be the same for all of them, so we're going to factor that out. It's the universal base. The height is the part that's going to be changing. All right. We get this universal base by taking the total distance and cutting it up into, in this case, 5 pieces, or however many pieces they tell us to do.
So the distance is 2.
So, right, so I would say it's always b minus a, the starting point, or the ending point minus the starting point, which is where you can look at it and say 2, over, in this case, 5. And then we're going to have each of these different heights based on wherever that spot is on the graph. Okay. begin with 2/5, that is the universal width. Okay, or the base length. Okay, so for our first one, if we start at -1 and make sure the base is 2/5, okay, that's gonna put us here at -3/5. Is that right? Yeah, -3/5. So rectangle number 1 is gonna go from -1, 2/5 over to -3/5. This rectangle will be going down. R5 means we're gonna use the right side of the rectangle to determine where the rectangle stops. So this first one will stop here. The rest of the rectangle will look like that. Okay?
So about extra.
So we'll have extra wasted space. It will be too negative,
Yeah.
is what it'll be, too much negative. Second rectangle is going to be 2/5 more over.
So,
Shouldn't be too bad.
So -1/5. This one will go down again, and wherever that one happens to hit, figure is not exactly drawn to scale, but you get the idea. Using the right side of the rectangle, that's where that one will hit. Go another 2/5 over, that'll be +1/5. And this one will actually go up, like that. Okay, go over 2/5 more to 3/5. That rectangle is gonna look like that. I put my 1/5 in a very bad spot. And then the last one is over here at 1, like so. So I'm looking at this going with 2 rectangles that are gonna use some negative area, these 2 pieces, and then these 3 right here, they're gonna use some positive area. Clearly, we've got some wasted space, like this negative area isn't even being included. We got a lot of extra positive area that should not be included that is being included. So we know this is not right, but it's a decent guess. Okay. F up. First rectangle went from -1 to -3/5. The right side of that is -3/5, so I'm gonna plug in -3/5. Second rectangle, -3/5 to -1/5. The right side is -1/5. And so on and so forth. What's the last one? 1? Okay, now it's just a matter of plugging numbers in and getting some stuff out. Not gonna be pretty at all. We're dealing with some fifths and we're dealing with some fractions and squares. Okay. Well, 2/5 is nice. Okay, -3/5.
do you want to have a calculator just
For the final answer, yeah, if anybody wants to crank
You
that
can
one.
use
I mean,
that
like,
one
we
to
don't-
record. That's what I was wondering, is that one recording too?
I don't know. I think
You
Mr.
said it
Parker,
was.
I think Mr. Parker might come in here and turn it on. I don't know if we're actually recording or not. Go check if we are, hit the record button.
I see a light.
I think
Lights are
we
normally
might
good.
be.
I think we might be.
Well,
But I'm
we
not
are
sure.
talking into the camera now.
Yeah, we are.
We are recording?
Oh, it's carrying. Cause I saw the little red dot and I was like, I think we will.
Okay, -3/5. That's gonna be 9/25 minus 3/5, which is 15/25, so -6/25.
What were you doing with this thing?
What do you mean?
So fancy. What are these degrees?
Oh, yeah, minutes
Inches.
minutes and seconds, yeah.
God.
Isn't that awesome?
What is this?
Stuff that your brain can't do.
It's not that hard.
I've never known this before though, so it's...
I'll show you later. Number 2, let's see, -1/5
Yeah.
squared is 1/25. 1/25 minus 1/5, or 5/25 negative 4/25. You keep a running tally of this. Ugly too. Positive 1/5, 1/25 plus 1/5, 6/25. Oh, that's nice. 3/5 is 9/25 plus. What is 9/25 plus 15? 24, 25th, 24, 25th. And last but not least, thinking one, we get 2. That was convenient. I'm gonna call that 50
Yeah.
over 25. Okay. Cancels. That is 20, so 70 over 25. Okay. We're gonna have 2 25ths or 2 fifths, and then 70 over 25. Equal 114, I think.
Yeah.
So we're gonna get 28 over 25.
Which, a little.
A little over 1. Now, that doesn't mean the total area is actually 1, that means there was about 1 more positive area than there was negative area. So some of this negative canceled out with some of the positive. It's not exact, but decent
Whatever
enough.
has like how much negative area and how much positive area.
That will be something that'll trip a lot of kids up, the way they word it. They'll either say, what is the area under the curve, which is what we just did,
Yeah.
or they will say, what is the area between the curve and the x-axis. In that case, they want all your area to be positive. So you would actually take this stuff and make that chunk positive, and then make the other stuff, leave it positive, and
Okay.
get a big total area, like net area. It's the same thing as when we do particle motion and they say total distance traveled versus displacement. Displacement is the distance between starting and stopping. Total distance traveled gives you all the back and forth in between.
Yeah.
So a big difference there. There's a right example, a horrible right example, by the way, but if you can do this, you can do just about anything. All right, you wanted a midpoint, let's do a midpoint and jump into the good stuff. Oh, yeah. All right. I'm pulling this one from number 18. The function they've given us is the square root of x, pretty straightforward, and the interval is from 3 to 5.
Okay.
I'm not going to bother drawing a picture, this is a simple one, and on the AP test, I would not be drawing a picture anyway, that's time wasted. So let's do midpoint 4. Again, the M stands for midpoint, and 4 tells you 4 rectangles.
Okay.
So, what is my width going to be?
Oh, 2, so 1/2.
Good. And for them, I'll show you, it's the distance, 5 minus 3 over the number of intervals, which is going to be a half. Okay, think about it like this. Maybe drawing a number line helps. Here's the distance that I've got to work with. I'm cutting that into 4 equal pieces, like so. So these 4 slices would be at 3, 3.5, 4, 4.5. There are my 4 rectangles, 1, 2, 3, 4. And then they're going to be as tall as whatever the function tells us to do. Okay? Okay, tricky. G, not an F. What height am I going to use for the first rectangle?
Let's see, so 1/2. 3 1/4.
Good. First rectangle went from 3 to 3.5. What is the center of 3 to 3.5?
3 1/4.
3 1/4. So that's where I'm going to use for the midpoint of that first rectangle. 3 1/4, well, 13/4. Okay. Second one, halfway between 3.5 and 4.
3 and 3. Cool.
3 3/4. If I can't easily read it like these, the best way to do it is just take an average, add them together, divide by 2, and then that's your center point. So was that 12, 15/4? G of 15/4. I'm pretty sure the next one's going to be 17/4. This is 4 1/4, which is 17/4. And the last one will
4
be
3/4.
4 3/4 or 19 fourths. Okay, so there's the setup, and that's how we find midpoint, which is really your question, is how you determine which value it is I'm plugging in.
Again,
It's the exact middle.
really not pretty.
No, it's not. The 4s are at least friendly,
Yeah.
so I won't be divided by a radical, but the tops are not that great at all. Alright, clean it up. We got a half out front. G of 13 fourths. Well, I'm plugging this in here.
So square root 13 over 2.
2 square root of 15 over 2.
Square root of 17 over 2.
And square root of 19 over 2. And I'm getting these just by plugging them in. So I would reach for my calculator. I'll let y'all figure out why that's a 4. All these are the same denominator, and then you multiply by 2 there. So whatever Michael gets when he's done plugging it in. If this were multiple choice and it's 9 calculator, that's about as good as you can make it. If it's calculator, you honestly don't even need to do this much work. If it were calculator, I would have plugged this into the y equals and then pulled these numbers straight off the graph. So when he's doing it, while he's doing that, visually what's happening here, you got our square root function, and let's say this is rectangle number 1. You're finding the middle and going up until you hit that, and then creating a rectangle like so. The idea is that we have a little bit of wasted space on both directions. Some we're not including and some we are including that we shouldn't be, so that hopefully it averages out. Usually midpoint is better than left or right for guessing, but we've seen these numbers get pretty icky pretty quick. What you got?
3.99.
Give me 3.
Zero.
990. Okay. So roughly 4, give or take.
I have a
If
question.
4 is the actual answer, that'd be nice.
I don't think it is. Yeah. Go ahead.
So if you were doing right side,
Yes.
is it like 3.5?
If this were right side, my width would still be a half.
Yeah, it'd still be a half.
I'd be using the right side, so 3.5, 4, 4.5, 5.
Okay.
And if we were doing left, I'd
Start
be
at
using
3.
3, 3.5, 4, 4.5, and that would be
Okay,
it.
because I got that mixed up.
Does that help?
Yeah.
Does that help?
They're probably gonna be laughing when you see this, if you realize that, right?
We laugh at them, so
Yeah, it's true.
turn about it's fair play.
Okay, I get it.
The clouds part.
Yes.
Okay, any other questions on the, I want to put a fork in our left-right midpoint, because today I hope we can evolve to the point where this, as gorgeous as it is, becomes obsolete, hopefully.
Okay.
Alright?
Yeah.
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 Whoa.
Alright, clearing the board. So let's pick up kind of where we left off yesterday. Kind of.
I need to get my minutes.
Yeah.
I know where it is, I just gotta answer stuff.
It's time for us to start looking at no longer guessing, to figure out what the exact areas are. Let's do a little review of our summations, okay? If I'm doing a right summation within rectangles, okay? And we may need to pause a second for them to do like a little mini lesson on summation, but for now, we'll just put the formulas down. In this particular situation, we don't lock in the number of rectangles, we let it float. We'll just go to n of them. We found out that's gonna be, we're gonna add up, that's what the summation means. All the rectangles, this again, the k equals 1, the k stands for which rectangle you are at. So we're gonna start with the first rectangle, which makes sense, then do the second, the third, the fourth, all the way up to the nth rectangle or the last rectangle. And then once you've added all that garbage together, that's what we just did with our little 4 and 5 rectangle examples. We do a universal width, which is b minus a over n, where b and a are the ending and starting points, and n is the number of rectangles you're cutting it into. And the heights of these are determined by whatever the function value is. Alright. I am about to erase what I'm getting ready to put down. I'm going to leave that up there, but to draw them a picture. Okay. You got random shaped area. Okay, and this could be anywhere on the graph, doesn't matter if it's at 0 or if it's shifted over here, shifted over there, it doesn't really matter. We'll just say this is the random starting point A, it's the random ending point B. And so a slice or a rectangle might look something like this. And because we're using right, the argument will be the same for left, but let's just say right looks like this. So here would be the first rectangle. Excuse me. Here would be the second rectangle. And so on and so forth to the last rectangle. Okay, all that stuff in the middle. The width, right here, what we call our dx or our delta x, that's how wide each of our rectangles. So what we did was take this distance from A to B and divide it by the number of rectangles, the n there. So that's how we're getting b minus a over n. This part right here is what gets some people. This is where the right side of the first rectangle is. And we determine that value by starting at A, going over one step, and then evaluating that function. That's how we get that height. Start at A, go over one little bitty step, and then plug that into F. Start at A, go over, in this case, we're letting K be 1 because we're starting with the first rectangle, and then we plug all that crap into the function. As we step, second rectangle, we would start at A and then go over 2 steps. So if K is 2, we do 2 of these steps and then plug that into the function and keep going on and on from there until we get to the ending, which is the nth. Okay? And notice if K is n, if we make it to the very end, excuse me, this n and that n would cancel, and then you'd have A plus B minus A. The A's would cancel, so you just get F of B, which makes sense because that's the end of the line. Okay? And you can rewind that and replay that a couple times until it finally makes sense. Yeah. Okay, that's the part I'm about to erase, so we're all cool with that? We got the picture? Okay. The left one. This is probably the only time I'm going to write it on the board because the calculations work better for right, slightly better for right, but it's nice to see left and midpoint. I'll give you the easier versions. Same width.
Nice of you.
Yeah. Same width. Still evaluating the function. Here's the only difference. We have to do this because in our first rectangle we don't want to use this step. We don't actually want to go out a step. We want to back up and start here. So what this will do is back us up from the right side of the rectangle to the left side of the rectangle. And last but not least, midpoint. Again, universal width is the same. Here we don't go all the way back, we come back halfway between the two. Ta-da! There are the 3 formulas. For the calculations we'll do today, I'm going to stick with right, and the idea is that if right works, you can make infinitely many tiny rectangles on the right. Doing the same thing on the left or the same thing in the middle would give you the exact same value eventually. Once we get to infinity, that's when they become the same. Cool. And for trapezoid, there is not really a cute formula for this. I'm just gonna say average of left and right.
If left and right are the same, then
Right, yeah. So if these two eventually squeeze together, then this would vicariously get squeezed in between there as well. And for those that don't know what the average is, it's just, I have to write it. Yeah. Add them up, divide by 2.
Really?
You'd be amazed.
I had no idea.
I don't even know if I can see my face. Am I off screen?
Yep,
Off screen?
you're off screen. I see your arm, now I see it.
Cool.
Alright.
All right. We had some special cases with the summations yesterday. I'll go ahead and put those down, special sums.
Do we have that written down?
Yeah,
Okay.
your Gaussian sums.
Oh, yeah.
Gauss, one of those brilliant mathematicians ever.
He's an excellent man. He's an excellent man.
He is. Came a little bit later. I would imagine if he were alive when the calculus was being discovered or invented, discovered, that he would have had a much bigger role in it. He came about 150 to 200 years after the advent of calculus, so he built on it, made some pretty neat discoveries, but his contribution to math is not really calculus driven. Although, the thing about math, we come up with an idea and then we spend the next 1,000 years trying to make that idea better, shorter, easier, all that kind of stuff. He's kind of the reason that the math is taught the way it is, that we aren't doing calculus the way they did 400 years ago, because it was messy. Here are the ones that he gave us. If you are doing the sum as k goes from 1 to n of just k, this is the little story I told you all about the school, the teacher told them add up all the numbers. That ends up being n times n plus 1 over 2. Okay? Sacrifice my knees for you children. Yeah. Is this still showing up on the camera? Is it still within? Can you
Yeah.
see the whole thing? Very good. All right.
I
Yeah.
told my mom the other day that I don't know how, I was like, I know your niece has search, my niece killed me. Like whenever I'm on like the ground or something like that. I don't
I'm
know.
still relatively active. I'm not a complete couch potato.
I mean, I'm probably as far as walking, but when I like sit on my knees,
Yeah.
it kills me.
I think wrestling helped because I had to sit like this a lot in wrestling on your feet like that, so I kind of got used to this. Okay. There are others. The formula, the pattern does continue. The formula is actually easier for the top. As you go past this, these numbers have a nice formula. It's the numbers on the bottom, they get kind of screwy, and thanks to Bernoulli, one of the Bernoullis came up with a formula for that. We don't really need to go past this. If we have to, we will, but I'm hoping y'all can see the shortcut if we just stop here. That's the plan. If you have to go past this, then we're kind of in trouble.
Well, that's great.
Yeah. Two other little things I will point out. I won't call these the special Gauss sums, but they are special sums. Number one, all right, this one is kind of neat because you're asking me to plug numbers into a variable that's not there. It's kind of like a constant function. You can plug 1, 2, 3 in everywhere you want. There's nowhere to stick it. If I stick in 1, I'm just going to get C. If I stick in 2, I'm just going to get C. If I plug in 3, I'm just going to get C. How many times am I going to get C? For that problem right there, how many times would I just get the number C? Not infinite. You need to stop that a lot sooner than, don't say infinite, say n.
Oh, in the.
N times. You go from 1 to n, so you're going to get n C's. okay?
Mm-hmm.
Or Cn. And the other special case is this. It's not really a special case, but a cool one to note. All right, if you are taking a sum like this, where you have something being multiplied, so maybe this is k squared, and I stick a 2 in front, so 2k squared. Every single time I do this, I'm gonna get an extra one of these numbers. So 2 times 1 squared, 2 times 2 squared, 2 times 3 squared. This is like our universal width. We can just pull it out front. So a good shortcut to know is this.
So we were not used to.
So yeah, like you know how we factor our width out front and just leave it out there and then do all the different heights?
Because everything's gonna be times C, so you can just pull it.
Right, just everything will be C times this, C times this, C times this. Okay, there is us setting the stage, and again, rewind it and look at it as much as you need to, but I think this is a pretty good indicator for all of our, or a pretty good list of all the formulas we're gonna need. I get tingly and goosebumpy every time I teach this, because it is so awesome. Alright, let's see what we can do here.
Did you notice?
I did. Just didn't want to go over there and get it.
Oh,
Here's
You
the
ready?
tables.
oh.
I don't know.
Here's our function. Let's start simple. Okay, get all x squared.
Okay, go to Y squared.
And let's start simple with our zone. Okay. We're not going to guess anymore. We're actually going to find the area.
Whoa.
It's coming.
We will begin by picking one of our estimates, either left, right, or midpoint, and then we're going to take, the new step is to take that and head towards infinity. So pick one.
Right.
Very good choice. Right.
You've been saying that one.
Yeah. Okay.
I was gonna be pressed.
So let's turn this into this little formula here. All right, it is going to be the summation as k goes from 1 to n. And again, the k stands for the number of rectangles. We could stop at 3 rectangles, we could go all the way to 20 rectangles or 50, but the ultimate goal is for us to go to infinity. You're basically squeezing the rectangles into lines. And while we think of lines not having area, you're never quite making them lines, so you're minimizing as much wasted space as you can, in theory. All right, universal width. I'm going to write it all out for you. So 4 minus 0 over n, which is just 4 over n. And f of a, our starting point is 0, 0, plus k times 4 minus 0 over n. Okay, we good? Setting the stage.
Yeah.
All right, let's clean it up just a little bit. This is just 4 over n. And this 0 doesn't really matter. This is 4 over n. The function itself is something squared, so I'm going to plug all this garbage into something squared. And that something will just be k times 4 over n. Excuse me. Everybody cool so far? We good? Okay, now you can do some algebra to clean this up a little bit, but we will hit a point where we get stuck. So let's pause here and say, this is going to be the area. You pick an n, and I'll tell you what our guess is. We'll plug in the numbers for n, do the arithmetic, add up some rectangles, and that's about it. Let's jump over to calculus. This will give me the exact area if I let n go to infinity. So now it's calculus time. We're going to take the limit as n goes to infinity of all of this.
Where'd you get the square root?
The square, I plugged this into F,
Oh,
which
okay.
was something squared.
Oh, okay.
And that was just me, the zero doesn't really matter, and I took the rest of that crap and stuck it right there. Okay, now it's an algebra game. And then we'll do algebra, and then we'll do one more line of calculus towards the very end. Can anybody else see the slide problem that I see?
There's a,
What's going to infinity? N. We got this nasty k hanging around, so we need to somehow get rid of that k value. Okay,
Say K is one.
so here, k starts with 1, but then it goes
It's
to
just
other
keeps
stuff.
going.
Yeah,
Well, I'm trying.
It's also going to infinity.
yeah.
Oh,
No, it's actually going to n, but n is going to infinity,
Yeah,
so it's
so-
kind of riding the coattails of n.
it's just.
It is. going to
What?
infinity.
Okay, we can clean this up a little bit. Who gets the square?
the
Oh,
K.
K and 4N.
K and the 4 and the n.
And
So
don't
this-
erase it now, I'm not ready.
Put it back.
So we got 4 over n, and if I square all of this stuff, I'll have a k squared, and I'll have a 16, and I'll have
N squared.
an n squared. And these two guys right here will go together nicely. Okay,
Okay,
so I'll have limit as n approaches infinity,
alright.
sum, k goes from 1 to n. All right, the 4 and the 16 give me 64, and the n squared give me n cubed. Cool? All right, and the k squared is left over. Now, part of that looks good. I see this in there, okay? The snag is this. Well, that's good news, because this, which has nothing to do with k, is actually
I put this.
just some random constant, okay? So this little part right here is acting like our c, so we can just yank him out front, because he's not affected by k at all. Limit as n approaches infinity of 64 over n cubed times the sum as k goes from 1 to n of k squared. And now we can thank Gauss and Bernoulli for giving us this cute little formula right here. Limit as n approaches infinity of 64 over n cubed times that, okay? N times n plus 1 times 2n plus 1 all over 6. And that one little snag that we saw before is now not an issue because the k's are gone.
So,
You wanted the limit as n goes to infinity, well, I gave you a formula that has nothing but n's in it. Okay? Now, back to calculus. What do we do? How do we take a limit going towards infinity?
hey Daddy rule.
Handy dandy rule, fantastic. Okay, so is this a top bigger, bottom bigger, or powers the same?
Bottom.
Same.
Got one vote for bottom and one vote for same. Same.
Wait,
Same.
no, I see why. Never mind.
What do you say? Same? Bottom. She said bottom. And we got 2 votes for the same.
Yeah,
What
same.
did you say, Chelsea?
She said same.
Leave me hanging here.
I see
Why
what
are
I
you
did
changing your
wrong.
mind?
Because I see what at the top.
She understands I'm right.
Yeah.
No,
Michael
I
said
caught
it.
my mistake.
N cubed on the bottom. What's up top?
3n.
Which will be
3n.
n cubed. This n will eventually be n cubed. So we're looking
I
at
see
a
what
powers the same issue. All right. Now that we know its powers the same, how do we do that?
Well, we're gonna have to,
Look at the leading coefficients. Very
Yeah.
good. All right, now bottom's easy. What's the bottom coefficient?
1.
Six.
Six. Yeah, that one's one.
That one's
That one
six.
is six.
Whoops.
Okay. Now, you can multiply all this stuff out if you want to, however, I don't care about all of it. The only thing I care about is the first number, which is going to be 2. The n, and the 2n are gonna give me a 2n cubed, and the rest of the garbage I really don't care
And
about.
it's gonna be n squared.
So that 2 with the 64 gives me 128.
Which,
You okay?
Yeah.
You don't need a calculator.
I'm
Seriously,
doing-
Michael
I'm doing
needs a
it.
calculator?
Not Michael.
What is it then? Just write down.
What can we factor out of both of the top and the bottom?
Two.
A 2. That'll give me 64 on top
You can do one.
Free number the first place.
and a 3 on the bottom. Ladies and gentlemen, the exact area is
Ooh.
64 over 3, or
21
and a third. Yeah.
It is what
That's
you
why
were
we're doing it,
excited to
it's not
show us
that free.
yesterday.
Not really, I mean, this is awesome, but this is, if you have mastered the entire process with that one example, then you shouldn't be in this class. You should be somewhere else teaching this class or something. All right, to walk through it again, we started with a generalization. We used right. By the way, the limit would have worked out beautifully the exact same way, whether we had chosen left or right. However, the right numbers give us easier math. Algebra. This isn't really calculus, this is us just throwing in the step that we're about to do calculus later, the limit. Algebra. And then these are 2 special properties over here and over there for summation. And then here's our one line of calculus, true
Yeah.
calculus. All right, now, here's the thing. We have found the exact area of one function. The very specific function, x squared, on the very specific interval from 0 to 4. So now what do you think I'm about to do for our next example? Maybe a different function, maybe a different interval with the same function, whatever, okay?
You're gonna try and trick us.
Well, I won't say trick. What I want to try and do now is give you problems that will make a pattern emerge.
Okay.
That's what I want to try and do is more examples so you can say, okay, if I can compare this answer to that answer, I can make a pattern out of it.
And find our shortcut.
Hopefully find the shortcut.
Are we
And
gonna be
the
upset
shortcut's
with you
gonna
when
come
we
in
see the
state.
shortcut?
Do I?
Are we gonna be upset with you when we find the shortcut?
I don't know. A little, but you'll be more excited than
Okay.
you'll be a little upset. That's okay.
I do notice that we start with
I don't
x
know, the-
squared, and then we end up
Okay.
with k squared.
Like here,
Yeah,
okay,
and
pattern,
pattern.
good. Let's try this. I'm gonna try and squeeze it over here. Try to. All right. We've got room. To keep the work as limited as possible, let's leave as much of this the same. So let's still do x squared. Let's just change our interval. Let's say from 0 to 5. Does that work? Okay. All right. Let's not reinvent a lot of the wheel. Most of this work is already done for us. We only have a couple of numbers to tweak in here, so let's fix that. Okay, if I do this, then R sub n, it's basically gonna be the same thing except 5 over n instead of 4 over n. You okay with that? All right, so we're gonna have the summation. This k goes from 1 to n of 5 over n times k times 5 over n squared. That's just me pulling straight from here. The limit will be the same. So it'll be the limit as n approaches infinity of all that stuff. And you know what? Let's fast forward here. If I square this, I'm gonna get, what is this, 25 over n squared. And then I'll put that 25 with that 5 and get 125, we're multiplying. And this n squared with that n and get n cubed, and then k squared. If y'all need me to stop, let me know, but I'm trying to just, there's no sense in us rewriting every single step of this problem. Okay, this being just a number will come out front. So we're gonna have 125 over n cubed. And then the stuff that's left over is still that same formula right there. So n times n plus 1 times 2n plus 1 all over 6. Okay, now we can actually do a limit and get our answer. This is still handy dandy rule, and nothing really much has changed here. It's still cube on cube.
6 on the bottom.
We're gonna get 6 on bottom,
And then 1, 250.
250 on top. Which we can pull a 2 out. It's kind of easy. In fact, you could have done this. The 2 and the 6 will cancel and give you a 1 and a 3. So we're gonna get 125 over 3. 125 is only 5 times 5 times 5, so it doesn't reduce, and there's our answer.
I have a shortcut for anything for x squared.
Okay, Michael is claiming,
Michael. We've planned things before, and I normally plan things.
that he knows a shortcut for
x squared.
x squared.
Yes, just
Alright,
to any from any part of x squared.
okay, Michael. If I'm doing x squared on the interval from, let's say, 0 to 7.
Okay.
Actually, you know what? For them, let's say just 0 to 2.
Okay.
Michael's claiming that the area will be.
Can
Do it.
I make a guess?
Yeah.
8 over 3.
She says 8 over 3.
And, for 8 over 6. 8 over 6.
8 over 3 is right.
Yay!
Yeah.
Why 3?
I don't know. She said it. Try another one. X squared through the interval from 0 to 3.
27 over 3. What?
Smart pants. You said 27 over 3? Fix that.
Oh, okay. Okay.
Somebody else can fix that. She got 20, you got 9 maybe, yeah. I do like that you said 27, I know why you're doing that. I'm glad that you got 27 over 3, but that is 9.
Oh, now I understand. Okay, never mind, I'm stupid. Okay.
By the way, these are correct. These
Yes.
are correct,
Yeah.
okay?
I heard the 2 and plus 1.
Alright, so I know Shannon's got it.
Yeah, I got it.
You got it? Maybe, don't lie to me. Come on now. No?
Yeah.
Did you see it? Did you-
Yeah, I just forgot the
Word,
2.
but I actually don't see.
Shannon, my dear, would you be so kind as to explain to us what your shortcut, ooh, you know what?
I'm not good at explaining.
Okay. I can do
Did
it.
it fall over here? Boy.
I can do it.
I need to erase something. I hate to do this. Okay, y'all got your notes. Alrighty.
So just b over.
If our function is x squared, And if our interval goes from 0 to b, what is my area going to be, Shannon?
B cubed.
B cubed over 3.
I knew because I was looking up there and I was like 5 and 125 has something to do with it. And I knew it's gonna be over 3.
What was this one, 4?
Yeah.
4 cubed over 3, 5 cubed over 3, 2 cubed over 3. That's why you said 27 was 3 cubed over 3, which
Yeah.
is 9. So
I'm
okay.
sorry, it was just,
It's cool, whatever.
it just kinda came to my head, I can't do that simple math, I'm sorry.
So ladies and gentlemen, we have discovered the shortcut. If it is only x squared going from 0 to some number. So it's a shortcut, I'll give you that.
Only for X.
It's a kind of very specific shortcut. Huh?
Only 0 to another number.
Correct. Every single one of these, we started at 0 and went to some other number.
Wait, so we're for any distance.
So here are the questions that you should be asking.
What's next?
There's no difference.
What do we do for the rest
Does
of the
it
question?
change if it doesn't start at 0? And is there a similar pattern if it's not x squared?
I don't know, let's find out.
That is the proper response. I don't know, let's find out.
Or
Love
you
it.
know, here's your answer.
Love it, love it, love it.
I do an answer for one, but not the other one.
Okay, so, what, you think you know the answer to one of those two things?
Well, A to B, there's no difference.
So if I start at something other than 0, it doesn't matter?
No, because you're still gonna get, if, in this case, if you look up there, the 5n will still be 5n. If it's still, if you did 1 to 6, it's still gonna be 5n, and then 5n squared, so.
Let's
Yeah,
tackle,
if you don't-
let's tackle Michael's first. Okay. Put that somewhere safe. Great formula for a very, very, very specific case, but great formula nonetheless. All right. Let's do, okay, change one variable, and in this case, the starting point. We'll do his first, and then we'll change the function next and see what happens with that. So, what would happen if we were to change where we started? Let's say from 2 to 5. Okay? Now we already know that 0 to 5 is 125 over 3. Sorry, 125 over 3. So we got that answer somewhere in our notes, somewhere in our books. If Michael's right, then the answer should still be 125 over 3.
Wait, what? If,
You said it doesn't matter where I start.
no, that's not what I said.
That is what you said.
I'm saying the
That's what you meant.
distance
That's what
between those two, so you had to, it would be 3 over n, which would be, that's what I'm
Gotcha.
saying.
So you're saying the answer to this should be
It's-
27 over 3.
Yes.
Gotcha.
It's the, really it's distance cubed over 3.
Okay, so, alright, correction. The answer should not be 125 over 3. Clearly that doesn't make sense because we have less area. Glad you saw that. You're saying whatever that distance is, so as long as we know that's a distance of 3, then we can use the same formula, same little thing, and just say 3 cubed over.
Really just b
3.
minus a cubed.
So your guess for this answer is 9.
Yes,
27 over 3.
yes.
Alright, 9.
9. See, he's doing it too.
Okay.
You're getting excited, aren't you? No, why not?
Okay, let's set the stage here. Summation as k goes from 1 to n of b minus a, so 5 minus 2 over n, and then f of what?
5 minus 2.
F of what?
F of
2.
k.
2 plus k 5 minus 2 over n.
Oh, never mind, okay. Never mind.
Do you see what we're doing there? So this 2 is because it's our starting point. Why didn't we have anything there last time?
Because it was 0.
Because it was, we had something, it was just 0. All right, let's rock and roll. Gonna go, K goes from 1 to N of, let's see here, 3 over N. Okay, I'm gonna go ahead and plug this into F. F is something squared, and the thing we're gonna square is 2 plus K times 3 over N. Everybody cool?
Yep.
All right. We can go ahead and do a limit. Limit as n approaches infinity. I'm gonna need one more than this. We'll do what we can. All right, here we go. Limit as n approaches infinity of k going from 1 to n of 3 over n times. Okay, we gotta square that. 4. Okay, if we multiply these two together, we're gonna get 6. I wanna keep the k separate because of what I wanna do with it over here. So if we keep the k separate, this is gonna be 6 over n. Then we double it and we get 12 over n times k. And then this part is gonna be 9 over n squared k squared. So far, so good. All right, we can thank Michael for this one. Limit as n approaches, remember our final answer is going to be
No, it's not.
right?
No.
It's not.
I was disproven by you literally wrote the first line, I'm like, done. My answer's wrong.
It might.
No, it's not.
It's not.
It's not.
No.
Not even close.
No, it was when we did the 0 to 5 one.
When I wrote that,
Oh,
that's when
yeah.
he went, oopsie. Yeah.
Because when you did the 0 to 5 one, you just counted out because it was 0, so you just didn't put it there. So that's what I was looking at for my example, and then
Oh,
pretty much. I just
well,
feel
guess
like
we'll find out.
Oh my word. Okay, here we go.
Start crossing things.
No, well, all right, this is gonna be 12 over n. This is going to be 36 over n times k. And this is going to be 27 over n squared, n cubed, wait a minute, I missed
I
one.
did the 30.
That's squared,
Wait.
and that's cubed. I'm distributing
Oh,
this
okay.
to all that. There's your 12, there's your 36, and then this is gonna be 27, and then k cubed, k squared, excuse me. All right, so far so good?
Yeah.
Yeah.
Okay, by the way, the sum of 3 things is 3 things sum. So you can actually split this into 3 different summations and just do each one individually. It doesn't really matter. All right, here we go. Limit as n approaches infinity of. Okay, this is number 1, right here. This is a constant, so I will have 12 over n times the sum as k goes from 1 to n of 1. All I did was factor that out. Plus 36 over n squared times the sum as k goes from 1 to n of k. Plus 27 over n cubed sum as k goes from 1 to n of k squared. Okay, this is pretty easy. Here's a constant right here. That constant is indeed 1, so this is going to be 1 times n or n. So we're going to have the limit as n approaches infinity of, all this should be parentheses, right? 12 over n times n. The second one will be we know what k is, so this is gonna be 36 over n squared times n times n plus 1 over 2. And I'm pulling that straight from here. Okay? And then 27 over n cubed times n plus 1 times 2n plus 1 all over 6.
And then, okay,
Everybody good?
yeah. There's a lot of canceling.
Yeah, kinda. Let's take a limit. Okay. The n's cancel out and I just have 12. The limit as n approaches infinity of 12. 12. It never changes. Still 12. Handy dandy rule. We do end up with an n squared on top here
And square the bottom.
and an n squared on the bottom there.
2 over 30. 36 over 2.
36 over 2 or 18.
Yeah.
Is that right?
And the third one is 27 over 6 over 3, which is 9. So, that was part of the answer.
Well, the two cancel, we get 3 is 20, it's 9, got it, okay. So our final answer is 39.
That was part of the answer.
We were off a little bit.
By 30.
Yeah.
Right, a little bit. Ta-da!
Which is really weird.
Why?
Okay, never mind, it's not good.
It's really weird. You knew what you were doing. It's odd. It was close to what I was expecting, but not quite.
Yeah.
All right, imagine, if you could please, not drawn to scale, but imagine, the further out I go, the more this goes up like this. All right, here's x squared. Let's say 2 is here and 5 is here. That would put 3 right about there. Okay, here's the area that we were looking for. And again, it's not drawn to scale, but it's a really good visualization. So here's the area that we were looking for. Michael said this will be the same thing as just doing 0 to 3. Yeah, that seems close.
Well,
No.
we can check.
No.
Yeah.
Well.
So one thing we're gonna have to deal with is, oh, here's what we could have done. Novel idea. We could have gone from 0 to 5 and then gone from 0 to 2 and then cut it off.
Aw, man, that would have been smart.
Okay? Does that make sense? Do y'all see that?
Cannot be done.
That would just mean, oh look, 0 to 5 and 0 to 2 and then snip it off. Let's see if that actually works. What was 0 to 5?
25 over
3.
125 over 3.
And then.
8
And
over
what was 0 to
8 over 3.
Yeah, 8 over 3, and then lop it off. What's that gonna be? 117?
117 over 3.
117 over 3. 3 goes into 11 3 times, with a remainder of 2. 3 goes into 27 9 times, 39.
Aw, man.
I like doing that more than doing that.
You think?
Ooh, I
You
wonder
think?
why.
That right there is a little.
Do you see once again why 0, the unsung hero, is so special to us? Going from 0, the reason it would look nice is because that wasn't there, and if that's not there, that's not there. All that garbage right there. You just have this little dinky thing on the end. But okay, so let's go a little bit further than this. What if we don't start at 0?
Okay.
That's not a big deal.
We can still.
Start at 0 and then cut off the part you don't want. Much better way to do this, okay?
So if you did this on like the AP exam, would they just be like, what are you doing?
Yeah.
they'd be like.
In fact, if you did this on the AP exam, even with an easy one like that, they still go, what in the world are you doing? Because again, we're about, that takes you all of 3 seconds tops. Okay. But second issue, that's only a cube formula for
X squared.
x squared. So what should our next logical experiment be?
X squared plus something, or X,
Something X squared.
something X.
Okay, now something x squared is easy because something x squared is
Would
just
just be
gonna
times
get pulled out front.
Yeah, so it would really just be,
Does that make sense? Because if you put it in the summation, we just, okay, so we got an extra 2 here, fine, we're gonna yank it out front.
so then it
Whatever.
would just be that, so it'd be something B squared, I mean B cubed, because it would be pulled out front.
So a better experiment might be, let's leave x squared behind.
Okay.
Let's now think x cubed, or x to the 4th, or x to the 5th, or just good old x. Okay?
Okay.
All right, I think we've done enough of this. Do y'all have these in your notes somewhere so I can do some room? Everybody good? Yeah, you might want to have those memorized. You get the notes from somebody. We should take up a collection for those of you taking notes so that we can, I'd sell these if I were you. If they're pretty good notes, I would.
Oh, you can't
look
read
for them.
mine. Mine's too small.
Let me pull this over here, and then we will try our next example. All right, let's leave that there. Okay, here we go. I'm pleased, by the way, with the experimentation, the thought, the question asking, and the fact that you're looking for shortcuts, and shortcuts plural. We found one tiny shortcut for that specific case. We also took this to the next step and said, all right, you know what? Hey, let's go even better. What if I'm doing x squared on the interval from a to b?
Then it's just,
How did we do it on that last example?
we did B squared divided by 3 minus A squared.
The cubed, right? We did the b cubed. We treated it like it went from 0, and then we did the same thing with a and treated it like he went to 0, and then just subtracted out. That's us cutting off the tail of the area, whatever that is.
Yeah.
That's pretty good. So shortcuts upon shortcuts. Who doesn't love that? Okay, now, I love where this is going, I hope. By the way, after we do, say, x cubed, then we're gonna jump to stuff like sine.
Oh.
How hot is that? Yeah. All right, G. Where?
4.
2,
It's a little
7,
daunting. Let's do 3 for now.
Aw.
85.
We can do 4. Let's do that first.
Okay, let's do 3.
Okay,
Okay.
set the stage, please.
Isn't
All right, we're gonna set up our right Riemann sums. Okay, I'm sorry, I've used that word so many times now. Riemann, did we talk about Riemann in this class? Who Riemann was?
No.
Maybe.
Was he
I
the
think
guy that
so.
cut it up into weird shaped pieces and had weird shaped heights?
Maybe not.
I can't remember what class that. Riemann sums are what we're technically doing. The thing is, he didn't cut it up into uniform pieces.
Oh, yeah, we talked
He
about
cut it
Oh,
up
yeah,
into
yeah.
random length and then
Yeah.
pick a random spot in the middle. So when I say Riemann sums, I'm talking about left, right, midpoint, all that kind of stuff. Sorry, I can't remember which class I said that one in. Okay, b minus a over n, so 3 minus 0 over n. And then f of a, which is 0, plus k times 3 minus 0 over n. Okay. as k goes from 1 to n, that is just 3 over n. That's just k times 3 over n. We'll go ahead and plug it in and get k times 3 over n cubed. All right,
Okay.
limit time. By the way, this, again, is the area, the estimate for any number of rectangles that you want to, any concrete number you want to stop at. Once we take the limit going to infinity, we're now outside of guessing and we're into exact area. This is it, okay? Limit, n goes to infinity of the sum as k goes from 1 to n of 3 over n, and let's go ahead and cube all that stuff out. So we're gonna have a k cubed, and we're gonna have a 27 over n cubed.
So,
Is that right?
yeah.
Okay. Limit as n approaches infinity. The sum as k goes from 1 to n, this is going to be 81 over n to the 4th and k cubed. All right, let's do,
And then we can pull the,
good. As far as k is concerned, that's a constant.
yeah, and then k is,
And then we're going to be left over, I'll write this extra step here. We're gonna have the k cubed, and that one will be the last little shortcut formula we have.
which is.
So if we don't get it after this, we've either gotta make up another formula or get it after this. So we're gonna have limit as, oopsie, begin. N approaches infinity of 81 over n to the 4th. And our formula for this was n times n plus 1 over 2 all squared. And now that we've swapped out all of our k's for n values, it is limit time.
Yay.
So question, handy dandy rule, top, bottom, or same?
Same.
Good. It's hidden, but this one's same. That n times n is going to be n squared, but then when you square that, you get into the 4th, so we are looking at top and bottom being the same.
No,
Okay.
isn't it gonna be, so,
What is my top coefficient right here going to be?
1.
1. The n and the n give me n squared, square it, you get n to the 4th, but it's still just 1. So what, have an 81 on top,
And a 4 on the bottom.
and that's squared, so 81 over 4, which does not reduce.
Yay. Give me a second, I might be able to find the shortcut.
So we're just,
Looking for patterns now.
Pattern,
Oh,
almost
that
the
was
same
called.
actually.
The-
A little different.
3 to the 4th,
3 to the
No.
power 4.
power 4, and then divide by 4.
Okay, so do you think you have a generalization for x cubed going from 0 to b?
Yes.
B to the 4th divided by 4.
b to the 4th divided by 4. Does it hold true for this one?
Yes.
Hold true for that, and I'll go ahead and tell you it's gonna hold true for,
Now.
So it's like the
More
pattern's just
pattern.
gonna be taking whatever exponent is, adding, just
Question.
bringing it up one more exponent and then
wait,
adding that down.
wait,
Okay.
wait.
I like more
I'm gonna
patterns.
put a star by this one. So you're saying if we do, why be so nitpicky? Why don't we make it
And then
x?
n plus 1.
Wait.
Okay. I'm sorry.
Going
jumping in.
from 0 to b. So your claim is that the area is,
B.
B to, with n plus 1 divided by n plus 1.
That's what, yeah. There's a pattern, but, well, hold up. Because we don't know what n plus, we don't know what k to the 4th is.
Am I right?
but you're claiming, okay, you're claiming, without knowing k to the 4th, you're telling me that if I were to give you something like, why stop at 4? Let's go
Yeah,
crazy, okay?
That it seems that way.
You're telling me that the area is going to be,
To the 87
2 to the 8.
over 8
Okay.
whatever that number is.
Yeah.
That is correct.
Yay.
Math patterns, yeah.
Okay, yeah, y'all are excited. You remember that part where I said you're gonna be really thrilled and excited about the shortcuts and the patterns?
Yeah, they're pretty cool.
Okay, they're pretty cool. Now let's do sign.
Aww. Wait,
Yay.
sign. Trig.
You found a great pattern for
Excellent.
polynomials, yay!
Yeah, for
Now let's go for trig.
Now let's do trig and logs and exponential. Woo!
That sounds fun.
Okay, y'all take a moment to pat yourselves on the back because that's not easy to see and easy to come up with. I mean, with me, it is, but that's perfect. Look at how much work you've just saved. All these weird areas and we're not guessing anymore.
I'm not saying that we're better than Greasy, but
Y'all actually got a little about a half a day ahead. They had something over there. So this is the point. If I had had 20 more minutes with them, they would have made it to this part. They got this. They got all this. They are not, because we have extra time, they are not going to get what I hope you are about to do.
Okay.
Evidently, it's not going to happen right now. Okay.
What?
so confused.
I'm trying.
You're so confused?
No, yeah, what do you want from us? Is there more?
Okay, remember I told you that you were going to be both
Happy.
angry and
Yeah.
elated? This is the happy, this is the joyous, euphoric, we've been dating a week kind of feeling, all right?
Yeah.
No.
This
We're gonna
one
get to
we're
that
just gonna
married
feel-
for 8 years kind of life here in just a second,
Okay.
okay?
It's a good thing I have some Advil in my car.
I hope. No, that's awesome, that's really good. I will give you your mad props for that, that is really good that you came. They didn't actually come up with this. We didn't have time to explore what happens if we don't start at 0, but they saw all these patterns here. They'll get this quickly tomorrow, but this is really good
Yay.
for polynomials.
Polynomials.
Oh, man.
Trig, let's do it.
Trig, trig,
Trick, trick. I never done trick. This isn't fair. I don't want trick. I should just
You just what?
I should just learn trick.
Yeah,
All of it.
probably.
Should probably take an online course for trig.
Might be
Really
nice.
fun.
Trigonometry.
Okay. Start easy.
Or you could just tell me when you're teaching your algebra 3 kids trick and then I'll come in.
Right now. Today's our first day of trig.
Are you serious?
They're learning right triangle trig. It'll be
Do I know that yet? Should I know that?
sines, cosines, and tan, like sine is opposite over hypotenuse.
Oh, yeah, I know.
That-
Yeah.
That's what we're doing now. We'll spend about a week and a half doing, here are the triangle relationships, sine is opposite over hypotenuse, and yada, yada, yada. I don't think we get to the hard stuff, like law of sines and law of cosines for the 2 weeks. And then about a week and a half after that is when we start graphing, so that
Okay.
might be, we're doing.
Just tell me when you get to the hard stuff and Miss Baker doesn't
Unit
care.
circle?
I know most of it. I have most
Unit
of it.
circle is early next week, like Monday or
Okay.
Tuesday. Just poke, if you're at Miss Baker's room, poke your head in the door and look to see what we're doing, and if it's stuff you don't know, then come on in.
Yeah, right.
We'll start out kinda simple. Alright.
Oh!
Woo!
I like pie.
Mmm. Oh, here, I'll start you out.
Thank you. We appreciate it.
Okay. The normal stuff, the fancy E, the Greek S.
And then
Ew.
pi minus 0 over
Good.
n.
K, and I, no, yeah, 0, it's K.
Okay, that's your last line of easy.
Aw.
Nah.
Aw.
Alright, pi over n,
Just now it comes to sign.
sine of
K.
k
Fine.
pi over n.
Okay, I like it.
Oh, that looks,
That looks,
oh.
okay, so,
How do we find pi k? I mean sin
oh.
k. And c.
Is it
Uh,
right side?
I don't know.
That's
No.
I'm guessing. How do you get rid of a sign?
No.
No.
Do we do something the same before we bring the k out?
That's a good, well, alright, here I can do this. That's legal.
Bam. It's out of there.
Yeah.
Get on out of here.
The rest of that
Scrub.
is just, unless I want to special ones either.
This is our
Dang
town
it.
screw.
Do you have a special one that helps? We don't.
Just polynomials, dang nabbit.
Maybe,
Are there ones for cheap?
I want, yeah, maybe. Does the all masterful Mr. Floyd know any trig?
100.
Do you know trig for this?
Yeah. I'm not gonna show it to you.
You'll feel bad for us eventually.
Mhm.
No?
He loves
Here's my hint to you, and this is where we're gonna end it today. This will be the end of the lesson. The rest of the time y'all can spend on your quests, okay? Let me just say this about trig. We haven't done anything wrong. It's a beautiful setup. Why is this one giving you trouble now?
Is that one?
'Cause we don't- that.
Yeah, how to deal with that?
We don't know how to get K out.
Right, we don't know how to turn a K into some N's and get it out and do that. Alrighty, I'll tell you this, we don't need to know how to do it because there is another pattern, another shortcut that, how to word this, that will help us realize that we don't need to do this,
Okay.
okay? Now, parting thoughts while you're working on your quest or doing whatever you do. This is way more important than you are giving it credit for,
Great.
okay?
Okay.
Once you find out or once you realize what that is, that's easy. So, those are my parting thoughts for the day.
Once you
Once
know-
you realize what that is, that becomes unnecessary.
It is part of our homework.